Hello everyone. So in the previous lecture videos we discussed about timer 0 programming, in which we have analyzed a programs for with respect to timer 0, wherein we have calculated the total time delay that is being generated by a given program. We also calculated the square wave of a particular program that is being generated. We have also written a program wherein if you know a particular time delay that needs to be generated by a program, or if you know the square wave frequency that needs to be generated by a particular program, we have calculated the value for timer H and timer L, and we have fed that into timer H and timer L, and we have programmed it. And we have also programmed it for 8-bit mode also. So if the time delay that needs to be generated is very low, then we can go with timer 0 program in 8-bit mode. We have also used the prescalars, wherein if the time delay that is generated with 16-bit mode is not sufficient, you can go with a prescalar option. So we have a prescalar from 1:2 to 1:256. So with respect to that, we can have a higher time delay and a smaller square wave of a frequency. So in this video, let us discuss about timer 1 programming. Timer 1 programming is basically again of 16-bit mode programming, and in this case, unlike in the case of timer 0, this will not support 8-bit mode of programming. So this is only for 16-bit mode of programming. Timer 1 will not support 8-bit programming, 8-bit mode programming. It only supports for 16-bit mode of programming. And unlike in the case of a timer 0, where we have a prescalar of 1:2 to 1:256, here we only have prescalar supports for 1:1 to 1:8. So since timer 1 is of 16-bit, we have a value for timer 1L and timer 1H. But unlike in the case of a timer 0, we can't use timer 1L separately and timer 1H separately. So we have to use the timer combining the value of timer 1H and timer 1L. But in the case of a timer 0, we can either use timer 0L or the combination of timer 0H and timer 0L. So timer 1 is basically a 16-bit mode programming, wherein you have to feed the value of timer 1H as well as timer 1L. So just like in the case of a timer D0 control register, we have timer 1 control register. So this is also of 8-bit. So of this 8-bit, one of the bit is unused, or it may be kept for future reference. So we have RD16, that is D7th bit. So 16-bit read write enable bit. So this can be used either to set 1 or a 0. So if you set it like a 1, so all the 16-bit can be expressed in one 16-bit operation. And if you set it 0, the timer 1 16-bit accessed in two 8-bit operations. So of course we have a 16-bit mode of operations, so it can be accessed either in one 16-bit mode, or it can be accessed in two of 8-bit operations. And this D6 is not used, or you may think like it's been kept aside for future reference. Then we have T1 CKPS1, T1 CKPS 0. So these are the timer 1 prescalar selector bits. So we have timer 1 prescalar selector bits from 00, that is 1:1, to 11, that is 1:8. So we have prescalars from 00 to 11. So you can have any of this between. Then we have timer 1 oscillator enable bit. So you can either enable the oscillator or we can disable the oscillator. We have timer 1 synchronization bit. So this timer 1 synchronization bit can only be used when timer clock source is of external. So this is going to make sync if timer 1 takes are coming from the external bit. If the timer clock source is internal, then this bit is of unused. So you can't use this bit if the clock source is internal. And this D1 bit is a clock source, timer 1 clock source. Timer 1 clock source can be internal or it can be external. So just like in the case of a timer 0, the clock source can be internal or it can be external. You can set 1 for external, 0 for internal. And the last bit, or you can think like a first bit, the D0 bit, so it can be enabled or it can be disabled. So 1 for enable, 0 for stop. So initially this bit will be 0 so that we are making the timer 1 declaration in an stop mode. And whenever you want to start ticking the timer, you can set this bit as 1. So the moment this bit is set to 1, the timer starts ticking. So you can pause the video and please take a look at this so that we can use this timer 1 control register in a programming. Okay, so just like in the case of again a timer 0, we have the interrupt register for timer 1 also. So in which case whenever a transition occurs or whenever the maximum count value has been reached, so in the case of timer 0, we have interrupt control register timer 0 IF flag which will be set to 1 whenever the count reaches from FF to a 0000. So timer 0 interrupt flag will be raised. So just like the timer 0, we have a timer 1 flag here. So this timer 1 flag will be set to 1 the moment count goes from FF to 0000. So whenever the transition occurs from FF to 000, then the timer 1 IF flag will be set to 1, indicating that the count has reached to its maximum value. So unlike in the case of timer 0 where we have int con register, this is PIR 1 register. So that is peripheral interrupt register 1. So we have more of these peripheral registers. We'll take a look at these register bits once we start with interrupt chapter. So please take a minute to analyze this register. So with that, let us try to analyze the program. Find the frequency of the square wave generated by the following program if crystal is of 10 megahertz. So here the crystal is being given with a 10 megahertz. So crystal frequency is of 10 megahertz. In your calculation, do not include the overhead due to instructions in the loop. So we are not concerned about what time taken to execute each of these instructions. So total overhead we are not considering. So what we are considering is we have a crystal frequency of 10 megahertz and we have a value for T1 con and the value for timer 1H and timer 1L. So with this, let us calculate the frequency of the square wave that is being generated here. So to calculate the frequency of a square wave in here, so we have the value for timer 1H and timer 1L. So we can subtract this value straight away with FF. So FF minus 7634 plus 1. So if you put this value into the calci, so if you put the values into the calci of a programming mode and in the hex mode, so we have FF minus 7634 equal to this value plus 1. So this gives us 89cc. So this is equal to 89cc, and this is again equal to in decimal 35276. So this is equal to 35,276. So we can write it like 35,276. So we have a 10 megahertz of crystal frequency, wherein if we have 10 megahertz of crystal, then we have 1 divided by 4 into 10, and each instruction will be executed in 0.4 microseconds. So in the same way, we multiply this with 0.4 microseconds. If you multiply this with 0.4 microseconds in decimal, so we have the value of 35,276 into 0.4. So that gives 14,110.4. So we have 14,110 microseconds, and if you divide this by 1,000, so you get it like 14.11 milliseconds. So we have 14.11 milliseconds. So the time delay generated from this particular delay subroutine is 14.11 milliseconds. But we want to calculate the frequency. So if you want to calculate the frequency, it's just inverse of this, that is 1 divided by 14.11 milliseconds. And since this 14.11 milliseconds is either for the negative edge or for the positive edge, that is half of the cycle, so we have to multiply this with a 2. So if you multiply this with a 2 in the calci, so what you get is you get 28.2208, and if you take the inverse of this, we have 0.035 kilohertz, and if you multiply with 1,000, we have 35.43 hertz. So in that case, this particular program delay subroutine is going to generate 35.434 hertz. So this is a frequency of a square wave that is being generated from this particular subroutine. So please take a time to look at this calculation and analyze the program. Okay, the next one. Assuming XTAL, that is the crystal frequency, is of 10 megahertz again. So write a program to generate a square wave of 50 hertz frequency on pin port 5. Use timer 1 in 16-bit mode with a maximum prescaler allowed. Okay, so first thing is we have to calculate what are the bits for timer 1 control register. So with this value, when 16-bit mode with the maximum prescaler allowed, so what we have is T1 con timer 1 control register is equal to 0x30. Okay, so this we get it from the calculation with timer control register, where we are programming it with a 16-bit mode and other possible values. Then since we have a crystal frequency of 10 megahertz and the problem statement is been given with the maximum prescaler allowed, so what we have to do is the maximum prescaler that is allowed is 1:8 in the case of timer 1, but in the case of a timer 0 it was 1:256. So let us calculate the value for a 50 hertz of frequency. So to calculate that, first we have to calculate what is time taken to execute each of the instructions. So 1 divided by 4 into 10 will give you a 2.5, and 2.5 into the maximum prescaler allowed is 1 divided by 8. So if you put this in the calci, so what you get is 1 divided by 8 into 2.5 will give you 0.3125, and if you take the inverse of this, you will get 3.2 microseconds. So the time taken to execute each of the instruction with maximum prescaler allowed and with the 10 megahertz of crystal frequency is 3.2 microseconds. Then let us calculate the value for timer 0h and timer 1h and timer 1l for a frequency of 50 hertz. So if you want a frequency of 50 hertz, so we have to calculate the time taken to time delay. So that can be done for 50 hertz, like 1 divided by 50, that equals to 0.02 seconds, or we can have it like 20 milliseconds. So this is for a complete cycle, both high and a low. So let us again divide it by 2 so that we can have it for either high of the pulse or low of the pulse. So 20 ms divided by 2, that will give you a 10 milliseconds. So we have a 10 milliseconds of a delay in either in the rising edge or in the falling edge. So with that, we have 10 into 1000 divided by 3.2 microseconds. 3.2 microseconds. So that will give us the value of 3125. So 3125. So that is, if you subtract this with 65,536 minus 3125, will give you the value of 62,411. So this 62,411, if you convert into the hex, what you will get is, you will get F3CB. So this F3CB, F3 is higher and CB is lower. Okay, so this is the value which we have to feed into the timer 1H and timer 1L. So let us start writing the program for port B and the value of F3CB with a Tcon of 0x30. So let us start initializing the port B, pin number 5, as an output. So first thing is, we have to declare a pin 5 of port B as an output. So that's a pin where the frequency of 50 hertz has to be generated. In the program, let us start the program with declaration of a pin 5 of port B, that is bit clear flag tris B, 5. So what this does is, it's going to initialize pin number 5 of port B as an output. So pin number 5 of port B is an output. Then we have to send a value 30 into T1 con. So that is what it has to be written for 16-bit mode of a timer. So for that, we set the value of 30 to T1 con with the help of the W register. Move LW 0x30. So what this does is, it moves a value 30 into the working register. Then we move that value to the timer 1 control register. So with this, timer 1 control register has got a value of 30. Then let us move the value of timer 1H and timer 1L. So we have the value F3 to timer 1H and we have the value CB to timer 1L. So move LW 0x F3. So this will move F3 into the working register, and then move WF into timer 1H. So this moves F3 into timer 1H. In the same way, let us move the value into timer 1L. So move LW 0x CB and move WF timer 1L. So this is going to move the value CB into timer 1L. And as usual, so before starting the count, we have to make sure that we are making interrupt flag as a 0. So for that we have to write bit clear flag, and we know that timer 1 IF is from PIR1, that is peripheral interrupt register timer 1 IF. So this is going to make the interrupt bit of PIR1 as 0, and it also makes that next program can rise an interrupt. So once this is done, let us call a delay. So this is going to call a delay, and after that we are going to toggle a bit of port B. So what this does is, this thing has to make the frequency, if it is low, make it high, if it is high, make it low. So thus creating a frequency of 50 Hertz. Bit toggle flag port B comma RB5. So this is going to toggle pin number 5 of port B. Then once it's toggled, so what you have to do is you have to branch back to here so that it is ready for the next toggling. So we have to jump back somewhere here, and we can branch it with H1 here. So this is what is going to generate a square wave of this, but we also have to write a delay subroutine for this one. So we have a delay subroutine here. Delay is the one which will help you in generating the square wave of this one. Now delay, what we have to do is, the moment it causes a delay, we have to start the timer. So that can be done with the help of bit set flag T1 con timer 1 on. So in the case of timer 0, we made like timer 0 on. In the case of 1, so we make timer 1 on. So once the timer is on, what we have to do is we have to keep on checking whether it has reached to the maximum count or not. That can be again done with the help of bit test flag skip if set peripheral interrupt register PIR1 comma timer 1 IF. That is timer 1 interrupt flag. If this is not been set, branch back. So branch back and hold up here until the interrupt occurs. That is, if the transition occurs from FF to 0000 back, then this interrupt I1 will be raised. So until then, keep on repeating here. So once this is being raised, skip this instruction and perform the making off of the timer. So bit clear flag T1 con timer 1 on. So we are putting off the timer 1. So once this is done, we have to return back to execute this instruction. So after this instruction, we have to execute this instruction. So this will call the delay, and after delay, the compiler has to go and execute this one. So the compiler will understand the return, and it tells that the next instruction is next to the delay call. So return is the last statement which has to be there in a delay subroutine. So this will generate a square wave frequency of 50 Hertz. So please take a minute to analyze this program. Okay, so that is what we have a timer 1 programming. So timer 1 and timer 0 are both are similar, except we have a timer 1 control register and timer 0 control register. So you have to be very much particular about selecting the bits of timer 0 and timer 1. So let us start discussing about the next part, that is counter programming. So we know that if the crystal comes from, or if the crystal frequency comes from internal clock source, then we can use that clock source to generate a time delay. if the clock ticks comes from external pin, then we can use that signal for accounting applications. So that's what we have a counter programming. So in the case of a counter programming, the value of timer 1H or timer 0H and timer 0L or timer 1L will increment automatically. So whenever there is a tick from a particular pin, in the case of a timer 0, if the ticks comes from RA4, so timer 1H, so timer 0H and timer 0L is going to increment automatically. And in the case of timer 1, if the ticks comes from RC0, the increment is going to happen automatically. This is all being decided with a pin of a clock source. So we have timer 0 control register and a pin of a clock source. So if you set it like 0, then it can be used only for time delay applications, and if you set it for 1, we can use it for counter programming. So we have pin number 4 of timer 0, wherein the pulse comes in. So this pulse goes high. For example, if you're connected to an IR sensor and if you want to keep monitoring the number of people entering inside a room, so whenever a person passes through the sensor, this signal goes high. Okay, and after the person is passed, so that goes a low. This is taken as a tick to the timer. So whenever people are coming in, the clock goes like this. So this in turn increments value of timer H and timer L bit. So if you are using timer 0, the clock is RA4. If you are using timer 1, the clock comes from RC0. So port A4, and this is port C, pin number 0. So first, let us find out the value for this particular pin, and let us make comfortable ourselves with a counter programming. So here, find the value for timer 0 control if we want to program timer 0 as an 8-bit mode counter. No prescaler options are used. Use an external clock for a clock source and increment on the positive edge. So it's been given with 8-bit mode of counter without any prescalers. We have to use external clock source and increment on the positive edge. So with that, our T0 control register 8-bit goes with a value of 0, that is timer 0 is off initially. Then since it's of 8-bit, so we set 1 to make it like 8-bit, and clock source is an external, so we make it 1 again, and this is a positive edge, so we make it a 0. Then no prescaler, so we are bypassing the prescaler. We set this as 1, and if that is 1, the remaining bits are all 0. So this is timer 0 control is equal to the value of this one, so that is 0x68. So 0x68 is a value that needs to be sent to timer control register if this particular problem statement is being asked. So depending on the variation in the statement, this value is going to change. So as of this, so this is what is the value that needs to be fed. Okay, so let us write the program with the same thing. So assume that a clock pulses are fed into a pin T0CK1. Write a program for counter 0 in 8-bit mode to count pulses and display states of timer 0L count on port B. So we have to print all the counts on port B. So in this case, the value of T0 con is straight away 68. Okay. So this is what we have to feed a value into the T0 con, and we also know that port B is an output. Okay, so we have to feed the value to the port B, and since it is an external clock source with a T01, in that case we are getting a clock takes from port A pin number 4. So port A pin number 4 is an input. So this is where the clicks are coming. For example, if you have attached IR sensor to a pin number 4 of port A, so it keeps on giving you the ticks. So this is an input and this is an output. So let us start declaring with the pins. So we have bit set flag, so that we are making this particular pin as an input. So bit set flag trace A, comma array 4. So this is going to make this particular pin as an input. Then we have to make complete port B as an output. So that can be done with the help of CLRF trace B. So this is going to make complete port B as an output. Then we have to store 68 into T0 con. So that can be done by storing 68 into the working register, then into the timer control register. So for that we write move LW 0x68, then move WF T0 con. So this is going to store 68 into timer 0 control register. Then we have to feed the initial value to the timer 0L, since it is of 8-bit and it has to give us the pulses. Okay, so since it has to give us the pulses, we have to clear timer 0L flag. So we make timer 0L as 0 by sending a value 0 to working register first, and then we send this value to timer 0L. So you can also write directly without this with the help of what we have is like clear F timer 0L. So either of things are good enough. So you can try with this, or you can go with this one. So once the 0L is being cleared, so it's ready to take the counts. So as usual, again we must have the maximum count. For example, you want to make the buzzer on if 50 students have entered into the classroom. So if 50 students have entered the classroom, I want my clock to be stopped, or it has to give me a buzzer. So either of this. So for that we have to clear the interrupt, so that not previous program has raised an interrupt and stored just like that. So int con comma timer 0if. So this will clear interrupt control and timer 0if flag. So once this is done, let us start the counting. So bit set flag T0 con timer 0 on. So this will start ticking whenever we have a clock like this. Timer 0L will keep on incrementing. So whenever a clock gets high low, so it's go from 0 to 1 2 until we have the maximum value. Okay, so this is what it starts in. So once this has been started, we must also have to check what is the value that needs to be sent to a port B. So we know that whenever there is a count, it has to be sent to a port B. So to send the value to port B, what we do is we write move FF, so sending the value from one register to the other register. So move FF timer 0L to a port B. So whenever there is a count, so we send that value to port B. This has to keep on sending the value until it reaches the maximum count. So once the maximum count of FF has been reached and the transition occurs to 0 0, so we have to either stop the timer or we have to make on the buzzer. So bit test flag skip if set int con comma timer 0 if. So this will keep on monitoring whether we have reached from 0 to ff, that is 0 to 255. So once we have reached here, the clock will go to 00. When the transition occurs from ff to 00, interrupt 1 flag will be raised. So the moment interrupt 1 flag is raised, so we have to perform the making off of the timer. If not, branch back somewhere here. So we have to branch back here. Once the interrupt flag has been raised, it's going to skip this instruction and it's going to execute the stopping of the timer. So that is done with the help of bit clear flag T0 con timer 0 on. So this is going to stop the timer. So once the timer is stopped, we can start from the beginning, or we can put on the buzzers. So as of this, so let us write like a go to here, and this here has to be somewhere here. Okay, so take a minute of time to analyze this program. So with this, we have completed the timer 0, timer 1 in assembly language programming. In the next video, we'll look at into programming timer 0 and timer 1 in C language. So until then, thank you for being here.